Hey y'all! This week we'll be talking about Chernoff bounds, which are super useful tail bounds for sums of independent random variables. In order to prove Chernoff bounds, we'll be using something called the moment generating function. So in this short video, we will quickly define what that is. The moment generating function of a random variable x is a function mx, which goes from r to r, given by mx of t is equal to the expected value of e to the tx. It's called the moment generating function because the moments show up as coefficients in the Taylor series. Using the series expansion of e to the tx and applying linearity of expectation, we can write mx of t is equal to the expected value of e to the tx, which is equal to 1 plus the expected value of x times t plus the expected value of x squared times t squared over 2 factorial plus the expected value of x cubed times t cubed over 3 factorial, and so on. And now we see the moments of x sitting right here. We can also see this by taking the kth derivative of mx to the t and evaluating it at 0. In this case, it turns out to be legit to switch the order of the expectation and the derivative, so we get the expected value of the derivative of e to the tx, evaluated at 0, which is just equal to the expected value of x to the k times e to the 0 times x, also known as the expected value of x to the k. So this is why the function mx is called moment generating. A useful fact about moment generating functions is that they actually characterize the underlying distribution. That is, if two random variables have the same moment generating function, then they have the same distribution. As an example of a moment generating function and how it can be useful, let's consider a Gaussian random variable z with mean mu and variance sigma squared. The moment generating function mz of t, well, this is equal by definition to the expected value of e to the tz. And using the definition of the expectation, along with the PDF for a Gaussian random variable, this is equal to the integral of e to the tx times 1 over sigma root 2 pi e to the minus x minus mu squared divided by 2 sigma squared dx. Now, if we do some algebraic manipulation, we see that this is equal to the following expression. Now, I know a big nasty formula just appeared on your screen very quickly. If you're in the mood for it, you can totally go and check this algebra, but honestly, it's not super important for the point of this short video. But if you believe that this algebraic manipulation is correct, the important point is that this expression here is just equal to 1. This is because this is just integrating the probability density function of some Gaussian random variable. In this case, it's the Gaussian with this mean and variance sigma squared. Thus, this whole expression is just equal to this bit, which in turn simplifies to e to the mu times t plus 1/2 sigma squared t squared. Okay, so what is the point of this? So in addition of now seeing an example of a moment generating function, knowing the moment generating function of a Gaussian is actually useful because it almost immediately implies that the sum of two independent Gaussians is again a Gaussian. To see this, suppose that x is a Gaussian with mean mu1 and variance sigma 1 squared, and suppose that y is an independent Gaussian with mean mu2 and variance sigma 2 squared. Then the moment generating function for x plus y is by definition equal to the expectation of e to the t x plus y, which, using the independence of x and y, is just equal to the product of their moment generating functions. Now we can use the fact that we just computed the moment generating function for a Gaussian to write out what these are. This is e to the mu1 t plus 1/2 sigma 1 squared t squared times e to the mu 2t plus 1/2 sigma 2 squared t squared. And this simplifies to e to the mu1 plus mu2 t plus 1/2 sigma 1 squared plus sigma 2 squared t squared. Well, this is convenient. This is actually the moment generating function of a different Gaussian, one with mean mu1 plus mu2 and variance sigma 1 squared plus sigma 2 squared. Because moment generating functions completely characterize the distribution, this means that the sum of x and y is again a Gaussian random variable with mean mu1 plus mu2 and variance sigma 1 squared plus sigma 2 squared. Neat! As one more example of a moment generating function, which is going to come up again when we talk about Chernoff bounds, suppose that x is a sum of independent Bernoulli random variables. That is, let's suppose that xi is a 0-1 valued random variable, so that the probability that xi is equal to 1 is some p sub I. And moreover, suppose that x1 ... up to xn are all independent. We can calculate the moment generating function for xi. We have mxi of t is equal, by definition, to the expected value of e to the t times xi, which is equal to pi times e to the t times 1 plus 1 minus pi times e to the t times 0. This simplifies as 1 plus pi e to the t minus 1. Now, suppose that x is the sum of all of the xi's. Then we can calculate the moment generating function of x as follows. Mx of t is equal to the expectation of e to the t times the sum over I of xi. And now we can use the fact that a sum in the exponent turns into a product downstairs to write the expected value of the product over I of e to the t xi. And now we can use the independence of the xi to exchange the product and the expectation. So this is just equal to the product over I of the expected value of e to the t xi. But now this is convenient because here is just the moment generating function for xi, which we've already computed. So this is equal to the product over I of the moment generating function for xi of t, which is equal to the product over I of 1 plus pi e to the t minus 1. So why is this equation useful? Well, in addition of being a second example of a moment generating function, this equation is going to show up again in the next video when we talk about Chernoff bounds. So, see you there soon. Thanks for watching.